Okay, today we are going to explain the time domain analysis of the second order system. And before we explained the first order system, and we mentioned that the first order system has two important parameters, like DC gain and the time constant. And just refresh your memory, the first order system in the standard form should be like that: K tau S plus 1, that's the input. Let's call the input V of S, and that's the output Y of S. So the transfer function of first order is K over tau S plus 1, and we call K DC gain, and the tau is the time constant of the system. Okay. Today we are going to explain the second order system, and we are going to use also standard form. The standard form that we are going to use for the second order system will look like that. K omega n square over S square plus 2 eta omega n S plus omega n square. This is the standard form of second order system. The input is V of S and the output Y of S. K is called the DC gain. Omega n is called undamped frequency. Undamped frequency, and sometimes they call it natural frequency. And eta calls damping coefficient. And we are going to explain the meaning of each. But first, let's have a very simple example, and we check how to find this parameter when we have any transfer function.
So what's the symbol?
That's called eta. Yes. Yeah. You just you write it in this way, eta. Okay. All right. How can you find this parameter? Let's write the transfer function, something like that. S square plus two S plus 5. And let's say that we have here 15. So let's find omega n, k, and eta. The first, we are going to look for the omega n. So omega n square is equal 5, right? So your omega n is equal square root of 5 radian per second. 2 S is equal to eta omega n. So 2 eta omega n is equal to, and omega n is equal square root of 5. So 2 eta omega n is square root of 5 is equal to, cancel 2 with 2, and your eta will be equal 1 over square root of 5. If you have a calculator, you may calculate this in decimal. See what the value of 1 square root 5. 0.45. And this is unit. There is no unit. It's just unitless. So that's your eta. If you want to find K, the DC gain, so you have K omega n square is equal to 15. So your K is equal 15 over omega n squared, which is 5, so equal 3. So we found the parameter of the second order system. Of course, I will remind you, eta could have 3 values, right? If eta greater than 1, what we call it? Overdamped. We explained that before. Yeah. Eta, when greater than 1, it means overdamped. What does it mean, overdamped? Overdamped, it means that you have 2 real roots and the response of the unit step, it will look like something like that. That's when eta greater than 1. It means you have 2 real roots and they are distinguished. They are not the same. They are not equal, unequal. Like, for example, you say minus 3, minus 5. That will be, we call it overdamped, to look like that. And if you have eta equal 1, we call it critical damp. And it means that 2 equal real roots on the top of each other. They are equal. You have 2 equal roots, like minus 3, minus 3. And the response will be similar to the overdamp, but it will be a little bit sluggish. So that one is called critical damp. And for in this case, eta is equal a 1. And the roots are real and equal. And this one called overdamped. Yes. And the roots are real, but they are not equal. Yeah. In this case, eta will be greater than 1. You have another case when eta is less than 1. When eta less than 1, we call it underdamped. What's underdamped? It means you have 2 poles and they are complex. Means they have real and imaginary. Like, for example, you have this one minus 3 plus J2 and minus 3 minus J2. And the response will have oscillation, and this oscillation will be damped. In the end, it will vanish. We call this underdamped. In this case, your eta is less than 1. So it's like your eta, it's some parameter that tell you the type of the system without finding the roots. We have another case when eta is equal 0. When eta is equal 0, the roots or the poles of the system will be imaginary only, on the imaginary axis. The response will be oscillatory. Oscillation but no damping. So we call this one oscillatory or oscillating system. And in this case, eta is equal 0. And the roots or the poles are imaginary. So eta is the damping ratio or damping coefficient that define the type of the system without looking at the roots. But even if you try to check what are the roots of this one, use your calculator in the function one and check for the roots. That's you'll find the poles equal to, in this case, please check with the calculator. Minus 1 plus 2i and minus 1 minus 2i, complex. So if you do that, you'll find complex. But if you look at eta is less than 1. It's 0.451, less than 1, which should mean underdamped. It means even before you do the analysis or the simulation, you will check, you will see, you will know that the type of the response to the step input, it will look like that. Damped oscillation. When you say omega n, we call it undamped frequency or natural frequency. It means if you don't have real parts, in this one you have minus 3 plus J2 minus 3 minus J2. It has real parts and has imaginary parts. The imaginary parts responsible for the oscillation. Real parts responsible for the decay, exponential. So if you delete the real parts, you will get J2, so your 2 will be your natural frequency, undamped frequency. But when you add the real parts, then the frequency will be damped. And we can calculate it. Omega D is equal omega n 1 minus eta square. That will call it damped frequency. Radian per second. What means damped frequency? It means the frequency will be affected by eta and it will be changed. It will be less than omega n. Well, how I found omega d is equal to omega n times the square root of 1 minus eta square? Very simple. Let's go to the equation. This is the standard form. If I ask you find the poles of the system, what you're going to do? You are going to take the denominator and make it equal to 0. And what we call this equation or this denominator, it has a name. Characteristic equation or characteristic polynomial. So let's write now the characteristic polynomial and try to find the poles of the system. The characteristic polynomial of the system, call it delta S, it's equal to S square plus 2 eta omega ns plus omega n square. Okay, that's very similar to the quadratic equation, right? If you remember before, the quadratic equation a s square plus bs plus c equals 0, and then find the roots. How you find the roots? You know the formula? So the roots, we have two roots, minus b plus or minus b square minus 4ac square root over 2a. What's your a? 1. If you compare, a is 1, right? What's b? 2 eta omega n. What's c? Omega n square, right? So you will say that the roots minus b, it will be minus 2 eta omega n plus or minus b square, that will be 4, 2 times 2 is 4, eta square omega n square minus 4 is c, 4 times a is 1, c omega n square, and all divided by 2a. A is equal 1, so divided by 2. Okay, let's simplify it. So I have minus 2 eta omega n plus or minus, I will take omega n square outside the square root, so it will be omega n. So you have plus or minus omega n square root. What's left here? 4 eta square. The 4 you can take it out also, that's true. Take it and you have 2, right? You have 2. So what's left? Eta square minus 1 over 2. So we can simplify it more. Just let's write that, take it to the other page. Yes, I'll take it to the other page. Copy. So that's, our roots or poles of the system. I cancel the 2. So you will have minus 2 over 2 is equal minus eta omega n plus or minus 2 cancel 2 omega n eta. Okay. Now let's look at eta. Possible eta on equal 1, greater than 1 or less than 1, right? So first, let's say that eta is equal 0. When eta equals 0, what you will get? You will get the poles S1 and 2 is equal, that will be 0. So plus or minus omega n minus 1, which is j, right? So you got plus or minus j omega n. So it will be like that. J omega n, j minus omega n. So, and I told you in the previous page that when eta equals 0, you will have only imaginary, right?
Yes.
And the oscillation will be the response to the step input. So you have the input be oscillation, like sinusoidal wave, never decay, the magnitude constant. Okay, so that would be oscillatory system. That's corresponding when eta equals 0. And we call it oscillatory system. Oscillatory response to the step. Let's take now another case. Let's take eta equal 1. So eta equal 1. What you will get? Eta equal 1 to be minus omega n plus or minus omega n 1 square 0, right? So you have minus omega n. You got real, and you got to have two roots because it's quadratic, it's second order. So it will be minus omega n minus omega n. You got only two roots equal. So it will look like that. And the value is minus omega n. Right? Okay. And what the response will be, critical damp, sluggish sinusoidal, and this one will be like continuous oscillation. Now let's take eta greater than 1. If you have eta greater than 1, so you have S12 is equal minus eta omega n, it's a number, plus or minus omega n eta greater than 1, like for example 3, 4. So if you have 3 square be 9 minus 1 is 8, square root of 8 is real, right? So you will have two real roots and not equal, because they will have plus or minus 1 time the first root. The first root will be minus eta omega n plus omega n eta square minus 1. The second one will be equal minus eta omega n minus omega n eta square minus 1. So you have two real roots but not equal. So when you sketch, that's one root here, one root there, and the response will be like that. And that's over damped. So they call this over damped. Let's look for the last case. What happened when eta is less than 1? I will go back and I will write, this is my equation. S12 is equal minus eta omega n plus or minus omega n eta square minus 1. Now eta less than 1, let's say that eta equal, for example, 0.5. So you'll have eta square minus 1 will be 0.025 minus 1 minus 0.75. So it will be minus. So what I will do, I will say it's equal minus eta omega n plus or minus omega n. If I do 1 minus eta square, I multiply by minus inside, right? So that will be equal here your j, right? Because of the negative 1. So that will be a complex. That's why when eta less than 1, you will have complex root. Because I proved to you now that eta square minus 1 is a negative 1. We call this omega d. We call this omega d, the damped frequency. Why? Because always the imaginary root represent frequency. Why? Look at when eta equals 0, what you got? Plus or minus j omega n. So the frequency is j omega n. This one has frequency omega n. And then when I did eta less than 1, I got j omega n times 1 square root of 1 minus eta square. That's the new frequency I have. So when I sketch, it's oscillating, damped oscillation. The oscillation here will be less than the oscillation in the case when oscillating system, and the frequency of this oscillation will be omega d, which is omega n square root 1 minus eta square. That I explained last time. So that will be under damped. So let's write that's oscillatory, and this one critical damp, and this one over damp. It means there is no damping. It's over. It's finished. This one under damp. The oscillation is under damp, still damp. So these are the 4 type of response for the second order system. And how we find the response using partial fraction, as we explained before. But now we are going to focus on the last case, the under damped, when eta less than 1. We are going to look for the performance of such systems. Do you have any questions?
Doctor, what is damp, over damp, critical, and under damp? Damping, what is it?
What's the meaning of damping,
Yeah.
right? Okay. The meaning of damp, something that suppress some kind of motion. So you damp it. For example, I mean, if there is a spring and this spring is oscillating, and then you put your hand, you put pressure on it, so you stop this oscillation. So you damp the oscillation. Okay. You stop kind of motion. You damp it. And the damper, in the door here, you find sometimes they have like a cylinder on the door, and then when you open the door, you close it. It doesn't shut or open it quickly. It just takes time to be oscillating. So because this one called it damper, it damp the fast motion. So make damping. So it minimizes the oscillation, as you see it, till the decay. So now we are going to talk about the case of the underdamp, and we call it time domain specification. Time domain specification. Okay. For step input, what we are going to get? We have here the y-axis, x-axis, and let's say that this state will reach here. So this broken line expresses the final value of the response. Let's call it YSS, Y steady state. Okay, and let's say that we have like little tube about this set value. So this tube that you define the accuracy of it. Some people they use 2%, and some people use 5%. What does it mean? It means, they don't want exactly to reach YSS. It's okay if you are plus or minus 2% of the final value. And in some application, they have like bigger allowance, so they let it go for 5% plus or minus. So let's say that we're going to use like 2% plus or minus. So you are at steady state, you can have more than the steady state by 2% of this value. For example, if YSS is equal 1, so you might have it from 1.02 or to 0.98. So it's okay if it's between 0.98 and 1.02, it is acceptable that you reach steady state. And even you can observe this phenomena if you have a voltmeter and you are measuring, some kind of volt, and it should get it 12. You find 12, 12.1, 12.2, 12.1, 12, 11.9, 11.8. You find it's just like that. It's okay. So this is the tolerance that you allow. You call it allowable tolerance. Let's write the name of it. That's allowed tolerance. And YSS is the steady state value. Steady state value. Now let's look for the response. Start from 0 here. We'll go there. And then it will overshoot the value. Will not go to the steady state value for the underdamped. It'll go up. And then it go down. Till it decay. Well, let's look for the performance here. And it's different from some people use different definition for the time, for the rise time. For example, some they consider the rise time when it reached the first time the steady state value, like this is the first time it reached, right?
Yes.
Okay. This value, this time they call it TR. What's TR? Rise time. You may find different definition in different textbook. Some they take it, for example, it starts from 10% to 90% of the response. And some they say, no, this is the first time it will reach this one. It's a kind, you want to measure how fast the system respond. Okay. Another thing. Now, you look here in this response, the output reached the maximum value here. That's the maximum value. Let's call it Y max. It's also bigger than the steady state in this second one, but this is the biggest one. So we call it the maximum. And that's very important parameter. We want to know the maximum output you get and how much it's different from the steady state. So if you look the difference between the maximum and the steady state, you will see that this is the value. That's the first, that's the maximum value that the output response exceeds the steady state. True? They define it by overshoot. Overshoot, yes. Overshoot let's agree about the symbol for the overshoot. Some they call it OS, for example. OS. The overshoot. And the overshoot is equal what? Equal the maximum value minus the steady state, Y max minus Y steady state over Y steady state. You have to refer it to the steady state value. And if you multiply it by 100, you can make it percentage. Some they say, okay, what's overshoot percentage? It's Y max minus YS over YS times 100. If you use the equation Y max minus YSS over YSS, it means it's equal Y max over YSS minus 1. That's right. So it's just you can divide this value by this value minus 1, you can get the overshoot. And usually the overshoot is a less than 1, right? or it can be bigger than 1? That's the question. It can be bigger. Because, for example, if let's say that ys is equal 1, maybe y max would be equal 3. So 3 minus 1 is 2, 2 over 1. So it can be greater than 1. Okay? But that would be bad. If you ask, is it good to have bigger overshoot? No. Because, I mean, you want to reach YC state. Imagine if you are controlling position of a robot arm, and you want the robot arm to reach this value, to get this one. So it will go like that, and then be like that till it go. That's not good. But maybe it exceed a little bit. That's okay. Yeah.
So overshoot is an unideality.
Is what?
Unideality.
Yeah, but it's some character there in under them. Yeah, it is. But yes, that's true. But if you can minimize the overshoot, that will be good. Why? Because, I mean, you are reaching the C state value. But in other system, maybe you are not reaching exactly the C state value. So that's the overshoot. And what about the settling time? Settling time, it means when the response get inside this tube and never get out. So let's look at here. This is the first time enter the tube, right? Did it get out? Yes, get out there. Then you go here. Then it comes here again and enter the tube and get out of the tube. Here again, enter the tube, get out of the tube. At this point, enter the tube, got out here. Enter the tube, did it get out? Okay, it means, frank speaking, it reached the C state. Or it settled down, because it's inside the tube, never get out. So, we'll make a line here كده. So this value, we're going to call it settling time from 0 till it reach this instant. Call it TS, and TS settling time. Another important time that we have, the time for the first time we have the maximum value, Y max. So if you go to the time from 0 till this one, what you call it? TP.
What is it? Y max?
TB, yes, exactly. That's, I mean, the time corresponding to Y max. TB. Peak time. This is the time when it reached the maximum value. So these are very important parameter in your response. So you have the rise time, you have the peak time, okay? Peak time when you reach the maximum value. You have settling time. That's when your response enter this tube, never get out of it, means that always will be less than the maximum and the minimum value. Because when you enter here, I mean, just, okay, it's inside. Never exceed this value again. So you are in your boundary. It's within your limit that you impose in it, okay? And that's, I mean, I don't know if you do it in the lab yet. This, okay. So you know what I mean, man? How we calculate, okay? We can use like some kind of equation to of the system to find the value fit. I'm going now to write the expression, mathematical expression, how to find TS, TB, TR, and so on. You don't have to memorize. We'll get it in the when we have the exam. We'll give it to you. Okay. The first thing, the rise time. You know the rise time.
Yeah. Yes.
So the rise time equation, TR, will be equal pi minus theta over omega d, and theta is equal to 10 minus 1 A over B. Let me explain a little bit about the theta, how we'll get the theta. If you have an S-plane, that's the real part, and that's the imaginary part, the imaginary axis. And you got your pole here, okay? And your pole here, like, you got the real value, and that here you got the imaginary value. The imaginary value is J omega D. And this is minus alpha. I'm explaining how you get it now. But I mean, let me refresh your memory. Do you remember the first and second root of the equation? We said it's equal minus eta omega n plus or minus j omega n 1 minus eta square, right? That's the root. We call this eta omega n, we can call it alpha. So it'll be minus alpha plus or minus j, and what we call this omega n times the square omega d, right? Damped frequency, omega d. So this is minus alpha, and this is j omega d. You can also make minus j omega d, but I mean this is one pole. The other one will be the conjugate of it. If you connect to the origin of this plane, this is your theta. This is your theta. So how you find your theta? By finding tan minus 1 this over this. This is your A, and this is A. Your B, and this is your C. What is your A? Huh? Not J, it's omega D. Exactly. And what's B? It's alpha. So when you can write tan minus 1 omega D over alpha, where this is omega D and this is your alpha. You can find theta also in different ways. Some people, they like to get it from the cosine. What's cosine theta? Cosine theta is equal the adjacent over the hypotenuse, right? So it's B over C. What's B? Alpha. What's C? Exactly. But let's find C. That's very interesting thing. C is equal the hypotenuse square A square, right? So you have A square plus B square. That's your C square, right? Then you find the square root. What's A? A is equal to omega D, right? Square it here. So you have omega n square times 1 minus eta square, the square root is gone, plus B square. What's B is alpha, and alpha is equal eta omega, so plus eta square omega n square, true? Now let's just simplify. So you have omega n square minus omega n square eta square plus eta square omega n square, right? This one like this one, right? Will cancel. So what you get? So C is equal to A omega n. So when you sketch on the S plane, you sketch the pole, the real part, the hypotenuse. When you connect the line from this pole to the origin, what the length of it is equal to omega. Yes, the natural frequency. Okay. So some people, they like to get it from the cosine. Cosine is equal B over C. All right. B is equal alpha, and C is equal A omega n. And what's alpha? Alpha is eta omega n, true? Yes. So omega n cancel omega n. So cosine theta is equal eta. So eta is equal cosine minus 1. I'm sorry, theta is equal to cosine minus 1 eta. Many people like this because it's very easy, very simple. Theta. So this is how to find rise time. Pi minus theta, which is cosine minus 1 eta, over omega d. We're going to take a numerical example later, but this is one expression. How can you find TR from the equation? You can get it in the lab by measuring, the when it reached the first time. You can get it from the lab, and then you can get also from the equation. Right. We'll go to move to the other parameter, which will be TB. TB, what's TB? The time at a big time. It's the time where is y equal y maximum, right? So TP, that's equal pi over omega d. That's it. That's how you find the peak time. Divide pi over in radian, of course, omega d. And you know what's omega d? So that's the peak time. What else? We need settling time, right? And overshoot. That's what's left. All right. Let's find the overshoot. The overshoot that we said is equal y maximum or ys minus 1, right? You can get it also using the parameter of the system. It's equal the exponential of minus pi eta over 1 minus eta squared. This is, I mean, how you find the overshoot. The last one, settling time. Settling time, that where it reached the steady state or settled inside the tube, it's equal 4 over eta omega n. So these are the parameters that we are using. But as we explained, it depends on the tolerance you allow, you can get settling time. If you make settling time, you can make it 2% or you can make it 5%. In this case, that's for 2%. If you are using 5%, you'll get different value. You will get 3 over eta omega n. So these are the parameter of the system. Let's take one numerical example and check how can we get it, how we can get all these values. Okay. Example 1. Let's say that you have a system and this system has a damping ratio. Can you say damping ratio, damping coefficient of 0.6 and natural frequency 5 radian per second. The question is, obtain the following: rise time, peak time, settling time, overshoot. Okay. When the system is subjected to a unit step input, because I mean the response that I showed just on the previous page, it's the response to step, not RAM, not anything else. Response to step. So they want to make sure that the input step. I will give you 2 minutes, 3 minutes to solve this problem, and they'll check. So I will remind by the equation g of s, the transfer function of second order, k omega n square over s square plus 2 eta omega n s plus omega n square. So you can write the equation, right? Your omega n is equal what? You told me equal 5 radian per second. And your eta 0.6. So from omega n you can get omega n square equal 25. And this part 2 eta omega n to eta omega n is equal to times 0.6 times 5. That will be equal to 6. And k is equal 1. Nothing is mentioned. So your transfer function is equal to 25 omega n squared over s squared 6s plus 25. That's your equation. Okay. But you have the most important part giving to you omega n is equal to 5 and eta is equal to 0.6. These are the most important parameters that you need to finish the A. Now we want the rise time. What's rise time? TR. Exactly. So TR, what you remember TR?
Yeah.
What equal pi minus theta W omega, not W omega. Omega n or omega d?
Omega D.
D, huh? All right. So you have to find omega d first. Type. Do you know omega d?
Yes.
What's omega d? Omega n time 1 minus square, right? So that will be equal to omega n is equal 5 square root 1 minus 0.6 squared. Okay, somebody got it? 4. Oh, that's nice. 4. For what? The unit? Radian per second. It's still frequency. Okay. I got omega d. Theta?
It's
Cosine minus 1 eta. That's a nice expression. So it'll be cosine minus 1.6. What you got? 0.9? 0.927? Radian, right? That's excellent. Because I mean, if you do degree, you'll be wrong. You got to do it in radian. Why? Because you are subtracting pi. So now we can find TR, right? So the rise time equal to pi minus theta, which is 0.927 over omega d, which is 4. 0.5? 5? 36. And the unit? Second. Second. Okay.
Doctor,
Yes.
can you tell us the precision that decimal points?
Okay. The minimum 3 decimal. Yeah. And after this point, 3 digits. Yeah. Okay. So we got TR, right? So we are going to find TB. Oh, big time. Let's change the color. Do you remember what's TB? Pi, it's very easy. Pi over omega d. So pi over 4. Yeah. 0.785. That's right. Second. That's good. Settling time. Settling time. Yeah, we're using, let's say that you have to define. If nothing mentioned in the problem, take it 2% accuracy. Okay? If you mention, use the right form. So using 2%, you will have 4 over.
0.6.
No, I mean the formula. Eta omega n, right? So you have 4 over 0.6 times omega n. What's omega n? 5, yeah. 1.33, 1/3. Okay, we got the settling time. Okay, so what's left? Overshoot. So how you find overshoot? Exponential minus eta omega over 1 minus eta square, right? You observe that overshoot does not depend on the frequency, right? Does not depend on omega n or omega. It depends only on eta, the damping. Yes, okay. So let's find this value. So be exponential minus pi eta minus 0.6 pi over 1 minus 0.6 square, right? Okay. Okay, 0.095, right?
947.
Which, yes, rounded this one. That's round. And if you like to express overshot in percentage, multiply by 100. So what you get? 9.5%. That's right. And of course you can sketch it. Now you can sketch it. You can sketch it using Excel or MATLAB or anything. You can sketch it. You know what is TR. You know all the thing. Okay. Okay. Yeah. Yes.
دكتور اكس اللي هو settling time اذا ما كان 2 or 5% كيف حطلع معنا؟ كيف حطلع الرقم؟
This is for settling time for 2%.
يعني لو عطيت الدكتور غير
If you have 5%, you replace 4 by 3.
يعني
Yeah.
بس هم هذول الاحتمالات.
That's it. That's the only two cases that people use. Yeah, not less than that. If they ask you, we said unit step. Okay. What about if I ask you to find y max? You know how to get it? Okay. So overshoot is equal y max over YSS minus 1. So y max is equal to 1 plus overshoot time y steady state. What is the value of y steady state? The y steady state is equal to the DC gain time the input. Right? The input is 1 and the CC is 1. So what the output is state? 1. Because I said unit step M. Nothing mentioned about DC gain means 1. So 1. So now I can say that the y max is equal 1 plus 0.095, right? Times 1. So 1.095. So this is the maximum value of the output. Okay. In this example, you have a system as shown to the left. The output is y, the input is r. And the transfer function of this one in the forward path is equal k over s time t capital time s plus 1. When the input is 1 over s, means a unit step, the output it looks like that. The question is, what is the value of k and t so you can get this response? The value of k and t to get the response. So the first, when you start solving this problem, the first you have to find the equivalent transfer function for the whole system, because this is not that's not the closed loop transfer function. It's just this one. It's just in the forward path, right? But you wish if you can do that. If you can express the system by one block, the input is R of S and the output A Y of S. That's what you need. You cannot work using your formula that you use in second order system only on this one. This is not the overall transfer function. The overall transfer function is y over r. This is not y over r doesn't give you, because there is a feedback here, right? So how we do this? Okay. Let's find y over r first. To do that, I will say if you have g of s and you have output and you have input, and this is like r of s and this is y of s, and you want to find y over r. Okay. What is y of s? Y of s is equal g of s time this signal here, call it E of S, the error. What is E of S?
It's R of S.
It is R of S minus this, and this Y of S. So E of S is equal R of S minus Y of S. And Y of S, the output is equal the input times G of S. So Y of S here is equal G of S time E of S, which is equal A, R of S minus Y of S, right? This is your E. the input. That's how we find the output for anything. How you find the output? Multiply the input by the transfer function. So what is y here? Y here is equal this times this. And what's e? R minus y. And now simplified, so you have y equal g of s times r of s minus g of s y of s. That's a y of s. Move this one to this direction. So you have y of s plus g of s y of s equal g of s r of s. So take one as a common factor. Alright? So 1 plus g of s times y of s is equal g of s r of s. Accordingly, y of s over r of s is equal g of s over 1 plus g of s. So that's the transfer function between the output and input, the overall system. So if you like to put something here, you are going to put g over 1 plus g, right? What's your g in this example? Exactly, this is your g of s. So you will say g of s is equal k over s ts plus 1. That's your g. Well, the transfer function y over r that you wish to put here, you use this formula. So y of s over r of s is equal g k over s ts plus 1 over, that's g, 1 plus, right? 1 plus k s ts plus 1. All right. I like to multiply both by the denominator. I multiply here by s ts plus 1. I multiply all this by s ts plus 1. You know why I'm doing this? Why? To get rid of the a. I don't like fraction. So I'll get so let's multiply. But you know, careful when you multiply the whole thing. Some people just they forget multiplying by this. This will multiply cancel, right? So what you have only k on the top over. This by 1 will be s ts plus 1 plus. You multiply this by this, what you get k only, right? Now it's getting better without fraction. You have k, you have s ts, you have t s square plus s plus k. Okay. All right. So I got the final thing. That's what I got. If you like to put it in the form that you used, s squared doesn't have anything in the front of it. It was just s squared, right? So I would take t as a common factor. So I will say it's equal k, and t is a common factor. What's left? S squared plus 1 over ts plus k over t, right? And then I can have t here, right? So I'll write it in the end, y of s over r of s is equal k over t over s squared plus 1 over ts plus k over t. So that will be your transfer function of the system. I didn't start the problem, I'm just simplifying. So even if you wish, you can call k over t a, for example. But it's okay, you can leave it like that. K over t s squared plus 1 over ts plus a k over t. So you got the transfer function. Well, if I ask you here, what is omega n squared? Can you get it?
Yes.
Right. What's omega n squared? K only? No.
K over T.
Yes, omega n squared is equal k over t. And what's 2 eta omega n? Do you know why? Because we said before the standard form k omega n squared over 1 plus 2 eta omega ns plus omega n squared. This is the general form. So I'm just comparing. But don't confuse it because I mean this K not the same K. Okay, so you can call it anything, you know, this again, call it A capital. Just I mean only in this part, call it A capital. That's your gain, yani. That's your DC gain. Just not to confuse the symbol are used. Okay, so when you compare, omega n square is equal K over T, 2 eta omega n is equal 1 over T, and when you compare, this one is omega n squared, there is no, so this again is equal 1, right? You don't have it. Okay, but still, you know, I don't have anything. I just have variables, right? No numbers. What will help you? Here. Here, and when you look at this graph, this is the response. You can get many things from this graph. This is the response that it's a practical problem. When you look at the oscilloscope, you can measure all the things. What does 3 represent? The peak time. So you know the value of peak time. TP is equal a 3 seconds. What is 0.254?
The overshoot difference.
The overshot. It's a difference. And then you divide it by 1, so this is overshot. Because overshot equal a y max minus y steady state. So y max, this is 0.254 given to me. Divided by the steady state, which is 1, get the same. So overshot is equal what? So from the response, I got this information. This is a very good problem. It's not direct. So the response gave me the information about the peak time, the rise time, everything. So let me just copy here. So that's what you got. The problem is going to be solved using this box. You compare your equation by the standard equation, so you have expression for eta and omega n. You look at the output, the response, and you put numerical values for whatever you have. You don't have anything else. You should be able to use this information to solve a problem, to get your unknown K and T. Well, to do that, you got to know what is the expression of TB and OS as function of eta and omega n. We know that overshot is equal to exponential of minus pi eta over 1 minus eta square, right? And you know TB is equal pi over omega d, right? And omega d is equal omega n 1 minus eta square. Which one you will start first? You start with the overshoot or TB? No, I'm not going to start with TB. Because there's 2 variables. You have omega n, you have eta. 2 unknown. But OS has only, so it's better. Fine. Now I will start with this. I'd like to take it in a new page because we are going to do some math here. By solving these 2 problems, I mean especially the last one, you should be able to solve any second order system. Now I decided to use OS to get the eta because I know the OS, the overshot is equal 0.254 equal the exponential of minus pi eta over 1 minus eta square. You take len, all right. So you have len. But what about, let's find expression. We'll say overshot is equal to exponential minus pi eta over 1 minus eta square. Just make it in a symbol so we can find expression. Find len. Len overshot is equal, len, so the len will cancel the e. So minus pi eta over 1 minus eta square root. Then what you'll do? Cross multiply. I'd like to get this. No, I got square root by itself, so I can square it. So what is the square root of 1 minus eta square? Or I can square everything.
Square everything.
Okay, let's square everything. When you square this, what you get? Len overshoot square equal square by square eta square over 1 minus eta square. Okay. Now what you'll do? Now we can cross multiply whatever you like here. Okay. So when you cross multiply, what you get? 1 minus eta square times len square overshoot by square eta square. So you have len square overshoot times 1 minus eta square times len square overshoot equal by square eta square. Now I get eta square together, right? So I take this in the other part. So you have pi square plus len square overshoot all eta square equal len square overshoot. Can you find eta square now? So eta square equal len square overshoot over pi square plus len square overshoot. Eta will be equal the root, but this root could be positive and negative. All right, so we have to do it in a way that eta always will get positive number. There is no negative number for eta, right? So will be len, it could be positive or negative, I don't know, right? Overshoot over root square by square plus len square overshoot. So we got expression. So when you get it any time you have the value for overshoot, you can get eta quickly. So in our example here, eta is equal to len overshoot is equal 0.254, right? It's given from the graph over square root pi square plus len square 0.254. So let's put the number. What's the len of 0.254? Minus, right? So we'll put here minus. We'll put here minus because right. So make it positive. You have to. So 1.37 square root of pi square plus 1.37 square. True. We are going to get eta. So how I got eta? I got eta from overshoot by using this expression. It's better if you memorize this expression and use it all the time. Did you get it? 0.39 998. Yani 0.4 almost, right? Okay, let's make it 0.4.
Doctor, I have a question.
Yes.
Can we not solve it directly from the calculator? Do we need to do this?
No. How you do it by the calculator?
Solve
You have a way? Yani this is the expression you are going to use, you know.
the original one.
The original one is 0.254 is equal exponential minus pi eta over 1 minus eta square.
You move the 0.25 to the other side is minus, and you solve for x. Let's say eta is x in the calculator. You get the value of x.
Yeah.
Directly.
That'd be nice. If you know how to do it, do it. Yeah? I use this expression, but you have, that's fine. So you get the value for eta. Now I use the peak time, right?
Yeah.
The peak time, it's set 4 over omega n 1 minus eta square, right? Now 4 over omega n 1 minus 0.4 square equal the peak time, it was equal 3 seconds, right? From this equation I get what? Omega n. Somebody calculate, okay? If you have your nice calculator, get the omega n. Will be in radian per second. This is not a direct problem, by the way. There are many things in this problem. 1.45. You can review the numbers when you solve it at home. It's better. So now we got eta 0.4. You got omega n equal 1.45. Remember, I got this from what? The response curve. Then I go and I compare here. Omega n is equal 1.45, so I square it. So k over t is equal 1.45 square, right? And 2 eta omega n equal 1 over t, and so I have 2 eta is equal 0.4, right? And omega n is 1.45. So you got 2 equations and 2 unknown. The first, of course, I'm going to do that one, right? 1 over t, let me take this. So this is the equation that I'm going to solve. Let's get it there. I found eta, I found omega n. I'm going to use my equation in the top. That's what I have. So I will solve this one first, right?
Doctor, it's 1.14, I think, omega n.
1 point.
You wrote the equation for t.
No, he wrote it right.
No,
No, it's 4. It should be by.
Yeah. TP?
Ah, that's right.
Yes, it's 1.14.
Yeah, that should be by. Yes, that's true.
So 1.14.
1 point.
1.14.
Okay. So let's correct it here.
So T is 1 over this.
Okay. I think I will do this first to get t, right?
Yeah, it's 1 over this, it's 1.09. 1.096.
That's the answer.
Yeah.
Okay, this is your t. I found the t, so now I can find the k, right? K will be equal 1.14 squared times t, which is 1.096 times this.
Doctor, this is 1 over t.
No, this is 1 over. That's the answer.
Yeah. I advise you to, when you go home, solve it again. Maybe you'll find some error in numerical error.
It's 1.42.
1.42. Okay. So you found the unknown.